Hello, my name is Kanchana Silak from Suranari University of Technology, Thailand. Today I will present my research about multiscale simulation for molecular and material property of perfluoro and normal polyethylene oxide melt. The objective of this is to simplify the IH model for PO and PFPO determined by ab initio electronic structure calculation from literature and validate this IH model by calculating the conformational dependent property and to generate and equilibrate the fully atomic amorphous structure of PO and PFPO at the Bow density and predict molecular and material property. Recently, our research group had developed the multiscale simulation for amorphous polymeric material at the Bow density. This work I tried to apply this simulation method to study two polymers with similar structure of perfluoro PO and normal PO for comparison. We want to see how the structure and property of these two polymers will be from chain with all hydrogen and fluorine atom. The multiscale simulation starts from the refinement of the original rotational isomeric state or IH model from PFPO and PO, which are determined from ab initio quantum chemistry calculation. We propose the method to reduce this matrix size to T by T cycle weight matrix by including the third order interaction. To validate this new IH model from PFPO and PO, we calculate the conformational dependent property of single chain based on the IH theory and compare the result with experiment data. This can be done by matrix multiplication technique using supergenerator matrix as shown in this equation. The simple version of IH model derived from the ab initio quantum chemistry calculation can be obtained by negating the third order interaction. Then we reduce the original 9 by 9 to T by T cycle weight matrix. The original 9 by 9 cycle weight matrix from ab initio quantum chemistry calculation previously done by Smith and co-worker. Then we simplify the IH model to T by T cycle weight matrix as shown here. After we got the IH model for PFPO and PO, in order to simulate both systems with multiple polymer chains, we need to introduce non-bond interaction. In our case, we employ the Raynaud zone potential between the cosine bit. One bit is equivalent to 2 backbone units. Then the cosine polymer chain will map onto the second nearest neighbor diamond of 2NND like this. Large amorphous PFPO and PO both can be generated and equilibrated using a Multiscale algorithm in the discrete space. After that, the fully atomic model can be obtained by the reverse mapping step to recover the missing atom followed by energy minimization. Negative result. First, after we refine the IH model from quantum method, we then calculate the conformational dependent property, including the characteristic ratio, dipole moment ratio, and temperature coefficient, and we compare this result to experimental as shown in this table. For PO, the characteristic ratio gives quite good argument to experiment. Anyway, this IH model gives characteristic ratio larger than experimental volume, but gives smaller dipole moment. For PFPO, our IH model gives small volume of characteristic ratio than PO, but larger dipole moment ratio. After the reverse mapping step, here are the sample snapshot of amorphous PO and PFPO structure. The intermolecular radial distribution function or RDF for different pair of elements for PFPO and PO are then compared. The results suggest that PFPO has dense structure than PO. For the fully atomistic model, we then calculate the in-branch solubility parameter. The experimental solubility parameter is 20, which is close to our calculated volume. In addition, the solubility parameter of PFPO is smaller than PO. To relate the feature, we then calculate the neutron scattering structure factor, which is very useful in determining amorphous structure that is related to the packing of polymer chain in amorphous phase. The scattering curve is related to Fourier transform operator of the radial distribution function. The prediction and experiment in the position and the shape of scattering curve are in close agreement. Here is our conclusion. Thank you very much, and I'm happy to respond your question and comment.